Welcome back to group theory.
Step by step.
Today we'll be looking at the groups of order 18 through 21.
What? That says 17 through 23.
Well, yeah, but we don't have to look at every order. We can skip 17, 19, and 23 since they're prime.
Right, so there's only the cycle group.
Yeah, and then 22 is 2 times a prime. We showed in a previous episode that any double of a prime will just have the cycle and the dihedral group. So there's only a few interesting cases.
Okay, so let's start with order 18 and look at the Abelian groups.
Using the funtofinag!
That's the fundamental theorem of finite Abelian groups.
Yeah, every finite Abelian group is the product of cycles.
So we just need to figure out the factorizations of 18. There's an Abelian group for each one, but they might not be unique, so we should count the orders of the elements.
Hold on.
What?
We don't actually have to check the orders.
Wait, what?
It's time that I taught you the true funtofinag.
Why didn't you just do that in the first place?
Every finite Abelian group is the unique product of pp cycles.
Which means prime power.
Yeah, if you want to be boring. Every cycle can be made of pp cycles. Last time we saw that 2 cycles can multiply into a larger cycle if their orders have no common factor. So the 2 and 9 can combine to make the 18 cycle. What about this case?
The 2 and 3 can combine to make the 6th cycle, and we just carry over the 3.
Exactly. We only need the pp groups to create everything else. And they will be unique.
Right. We can't combine the 3s to make 9 since they share a common factor.
Yep. So now let's use the true funtofinag for orders 20 and 21. What are their pp factorizations?
20 has 4 times 5 and 2 times 2 times 5, so that's 2 Abelian groups. And 21 is just 3 times 7. There's only 1.
Nice. We now have a straightforward method for finding the Abelian groups. Although writing out pp groups takes up a lot of space, so we usually just write the combined version.
Makes sense.
All right, now we never have to find the Abelian groups again.
Goodbye, Abelian groups!
Now let's find the non-Abelian. We'll start with order 18.
Okay, there's D18 of course, but there's no quaternions since it's not divisible by 4. I'm not sure if there's anything else.
I agree.
Wait, you don't know?
No, I agree that you're not sure.
Why would you even say that?
What if we multiply smaller groups?
Oh yeah, we could multiply an order 9 times 2, or a 6 times 3.
The groups of order 9 and 2 won't work though. They're all abelian, so any product would also be abelian.
But with 6 times 3, we could do D6 times C3.
Yes, that is a new group. Although we should check to see if it's actually different from D18.
Let's count the orders of the elements.
Sure, but we'll make the computer do it. Please input generators.
What?
Generators, remember, like from last time, computers use equations such as r to the 9 equals Einheit.
Right. And then f squared is Einheit, and then fr is r inverse f.
Affirmative. However, we require letter format such as R equals blank, F equals blank, and FR equals R.
Okay, I get it. So for the other group, D6 is the symmetries of a triangle. So RRR is blank, and then FF is blank, and then FR is R inverse F.
FR equals RRF.
Right. And then for C3, we have AAA is blank, and then A commutes with R and F.
Thank you for the equations. Preparing bar charts. Bar chart prepared.
So they are different groups. D18 has no elements of order 6. It's mostly order 2 because of the flips. And then the product has no order 9. It's mostly order 3.
Please input generators for the following group.
The following group?
Yeah, we're not done with order 18. These aren't the only non-Abelian groups.
But D6 times C3 is the only non-Abelian way to multiply, so it must be something else.
It's the only way with the direct product. Last time we learned about
the semi-direct product.
Yeah, and we already saw an example in this video. D18 is C9 semi-times C2. But what does that mean?
It means that C2 messes with C9, right?
Yeah. C9 is the rotations, C2 is the flips, and the flips mess with the rotations. When rotation passes flip, it gets inverted.
Which means we can make non-abelian groups out of abelian groups.
Exactly. And it also means that we have to be careful about the direction. C9 messed up by C2 could be different from C2 messed up by C9. We need to check both cases. So then we should also check C3 squared semi-times C2 and C2 semi-times C3 squared, and then C6 C3, C3 C6, D6 C3, and C3 D6.
Wow, that's a lot.
But wait, there's more. In this case, C2 messes with C9 by inverting. R goes to R inverse. Then with this product, C3 messes with D6. F could go to RF, or it could go to R squared F. There are multiple options. For each semi-direct product, we have to check all possible mess-aroundings. Messing-arounds? Mess-arounds?
Can you just say the real math term?
Fine. Automorphisms.
That sounds like the term from last time. Isomorphism?
That's because they're closely related. To recap, what does it mean if two groups have an isomorphism?
It means they act the same.
Yes. And we have some map that can move back and forth between them. An automorphism is an isomorphism from a group to itself. Auto means self. So C9 has an automorphism by inverting the rotation. Both sides act the same.
Right. We're basically just switching from clockwise to counterclockwise.
Exactly. And this automorphism can be used to make a semi-direct product. It's okay if C2 messes with C9 because it will still act as C9. And that brings us to our first real-world application of the semi-direct product.
Oh, cool.
If you mess with someone, you must still let them act as themselves.
Sure, I guess, but that really has nothing to do with math.
I know, that's why I said real world. Getting back to the abstract world, a semi-direct product requires an automorphism. But not all of them work. C9 also has an automorphism that sends R to R squared, but it can't make an SDP.
Why not?
Let's try. We'll say that F applies this automorphism. So when R passes F, it gets squared. Now what happens when R passes FF?
After the first F, it gets squared, and then the second F squares again, so we get R to the fourth.
Yes, but now we have a problem. What does FF equal?
Oh, it's Einheit. The two sides are different.
Yeah, F squares to Einheit, so then the F automorphism must square to the Einheitomorphism, which doesn't do anything. It just maps R to itself. This fails with the square automorphism since R ends up at R to the fourth. But what about the inverse automorphism?
R goes to R inverse, and that goes back to R. It's the Einheitomorphism.
Yes, that's why it works as an SDP. So to find all the SDPs, we need to find all the automorphisms that square to the Einheitomorphism. And that might sound like a difficult task, but we can use the magic of group theory. Automorphisms form a group.
Wait, really?
Yeah, let's check the terms and conditions for being a group. First, we need an operation, a way to combine elements. And we can combine any two automorphisms. They go from a group to itself, so we can just fuse the middle G's. Like with C9, what happens when we combine the square and inverse maps?
R goes to R squared, and then that goes to R to the -2.
It's the squinverse map. Any two automorphisms combine in a similar way. So we do have an operation. The next condition is that we need a neutral element.
That's the Einheitomorphism.
Exactly. Easy peasy, nauseous beetle.
Nauseous beetle?
Lennon's queasy.
Ugh, what's the next condition?
Inverses. Every automorphism needs an inverse, like the squinverse needs a squinvinverse.
Okay, they should combine to be neutral, so R should end up being at R. We send R to the -2 to R.
Yes, it's the backwards version. Any automorphism goes both ways, so we can just flip it. There are always inverses. And finally, we need associativity, which is boring, so we'll skip it. It's a group. Wait, let's just say we covered it. What were we talking about before?
The semi-direct product.
Right. To find all the SDPs, we want to find all automorphisms that square to the einheitomorphism. The automorphisms of C9 are the group C6, a 6 cycle, which we can see here. These automorphisms have order 6, so they don't square to Einheit. And these have order 3, so they don't either.
It has to have order 2. F is the inverse.
It can be the inverse, but it doesn't have to be.
Oh, could it also be the einheitomorphism?
Yes, the einheitomorphism does square to the einheitomorphism. The F automorphism doesn't need to have order 2, as long as the order divides 2.
That makes sense.
So what group does the einheitomorphism make?
F applies the neutral map. So when R passes F, it's still just R. They commute. It's just the direct product.
Exactly.
So there are 2 possible SDPs.
Yes, but this one is Abelian, and this is D18. We haven't found a noop.
Noop?
New group. Maybe we can find a noop by flipping things around. C2 semitimes C9. What does this mean?
Now C9 messes with C2. So R should apply an automorphism to F.
Exactly. But the automorphisms of C2 act like C1. It's only the einheitomorphism.
So then R must commute with F. We only have the direct product.
Yes, and there's nothing special about C9. If we take C2 semitimes any G, the elements of G must apply the einheitomorphism, and we have the direct product. So how could we apply this idea to the remaining cases?
Here, there's a C2 on the left. That must be a direct product, so it's Abelian.
Yeah, that case is noopless. Where else can we apply this?
Nowhere, right? Nothing else has a C2 on the left.
Not at first glance, but here we can split the C6 into C2 times C3. The right group will mess with them separately.
Okay, so the C2 will just be the direct product. We only have to check the C3.
Yes, we'll say this one is generated by A and this by B. So B should apply an automorphism of the left C3. And the automorphisms of C3 are the group C2. We have Einheit and inverse.
So B can only apply the Einheit.
Why?
The inverse has order 2, but B has order 3. And 2 doesn't divide 3, so inverse to the third isn't Einheit.
Nice. B must apply the einheitomorphism, therefore we get the direct product. All the products are direct, so this group
Abelian!
Yeah, not a noob. But we can use this splitting idea in other cases. Here we can split the right side.
And we just showed that C3 semitimes C3 has to be direct.
Exactly. We just need to check C2. And this case is interesting since the automorphisms of C3 are C2.
So we can apply the inverse map. It's not direct. We might have a new group.
We don't. Let's say that C3 is generated by R and C2 by F. So then F inverts R.
It's the triangle group, D6.
Yeah, this is just D6 times C3, which we've already seen. But now we're ready for the noop. We can split this D6 into C3 semitimes C2. C3 semitimes C3 must be direct, but what about C2?
It could be the inverse.
Yes, and this is also the inverse, so they can combine. C2 applies the inverse map to C3 times C3. This is a noop.
Cool.
Input generators.
Oh, for the first C3, A cubed equals Einheit.
Did you intend A equals blank?
Yes, and then B equals blank, and they commute.
Proceed.
And then C equals blank, and C inverts A and B.
Preparing bar chart prepare.
Whoa, it's all orders 2 and 3.
Yeah, we can think of this as the symmetries of 2 triangles. But they're messed with by the same C2, so either both flip or neither flip. If they both flip, that has order 2, and if neither flip, that has order 3. And that's the final group of order 18. To summarize, each group is either a product of C3, C3, and C2, or of C9 and C2.
They differ based on the type of product.
Exactly.
What about the other SDPs?
Oh, yeah, we didn't cover these two cases. We'll leave that as an exercise for the users.
The users?
Yeah, the users of the video. It's time to look at the groups of order 20. We already saw the abelian ones. What about non-abelian?
We have the basic ones, D20 and Q20. Then we can multiply smaller groups.
Yes, but order 5 times 4 won't work, since those are all abelian.
We could do 10 times 2 using D10 times C2.
Yes, though this is not a NOOP. It's the same as...
D20?
Yes, D20 is C10 semi-times C2. We can split the C10, but then notice that we have an SDP with C2 on the left, meaning...
It has to be a direct product.
Yeah, so we can remove that. C5 semi-times C2 is D10, so we end up with D10 times C2. Direct products don't give us a NOOP.
Then we should check out the semi-direct products.
Yeah, here are all of the cases. Where should we start?
These ones have C2 on the left, so they must be direct products.
Yeah, they're NOOPless. And then these ones have C5 on the right, so the automorphism order divides 5. It can be...
1 or 5.
But the automorphisms of C4 are the group C2, which doesn't have any elements of order 5.
So it has to be the einheitomorphism. It's a direct product.
And the automorphisms of C2 squared are D6.
Also no order 5, so that's direct too.
Yeah, these are both NOOPless. But then we have C5 semi-times C4. The automorphisms of C5 are the group C4. The einheitomorphism, the square, the inverse, and the squinverse.
So we can use the square automorphism, since it has order 4. Is this a NOOP?
A equals blank. B equals blank. BA equals...
Oh, it squares, so AAB.
Gratitude. Preparing bar charts. It is a NOOP.
And it's only orders 2, 4, and 5. The semi-direct products seem to concentrate elements into small orders.
Yeah, that's an interesting point. D20 and Q20 are also mostly small, but they have some order 10. And then the abelian groups are mostly large. And actually, these are all of the groups of order 20.
Let me guess, you're going to leave those other cases as exercises for the users?
It's time for order 21. We saw earlier that there is just one abelian group. What about non-abelian?
21 is odd, so we don't have D21 or Q21. Maybe we can multiply smaller groups.
But that would have to be 3 times 7, and both are abelian.
So the product would be abelian.
Yeah.
Okay, maybe there's a semi-direct product.
There are 2 cases. As we've seen, the automorphisms of C3 are the group C2, which means...
C7 must apply the neutral map. This is a direct product.
Yeah. But in the other case, the automorphisms of C7 are the group C6, which we can see here.
The square map has order 3, so C3 can apply the square.
Yes, this is a NOOP, and it's the only non-abelian group. These are the only groups of order 21. And that wraps up this episode. Thanks to the recent supporters of the channel. You can learn further by exploring the Cayley diagrams and tables of these groups at the site linked below. We'll see you next time for the groups of order 24. And maybe 25. I'm not sure. I haven't planned the full scope of it yet. We will get to 25, of course. I just mean that I'm not sure if I will, I'm not sure if it's going to happen in the next episode. I don't know how long 24 is going to take, if it's going to need to be its own full episode like this.